We'd like to invite Danish Aerospace to the stage.
71% of the surface of the Earth is covered with water. 2.4% of that is fresh. And 0.007% of that is accessible to 6.8 billion people. And our population is growing. And this is one of the most resource-available environments that we can think of. It's the blue planet. But as we think about interplanetary exploration and the environments that we'll go to one day, the picture becomes a lot more stark and difficult. Here's some images with some resource-rich people. Some military forces that are charged with finding water in areas where there is no water here on the planet. And we can do it. We've got the logistics plans, we've got the people, we've got the materials that we need, we've got the equipment, all the technology behind we need to take from fouled water sources to make it into good water sources. We can bring water, truck it in, provide it to people that are going to experience a hurricane well in advance. We've got this one nailed. We can do it. But what about these guys? They don't have the same resources. These are everyday people around the world. On the bottom left-hand side of the screen, they're digging for water because their water ran out. They're digging large holes, spending up to a third of their day, taking gallons of water back to their families, and that's their existence. On the bottom right-hand side of the screen, you have a really fun scene where some kids are kind of looking at something funny in a jar. And the sad part is, that's the water that they're going to drink. They're like, ugh, this is what we have? And this is the thing that really hits home to me. I've got two boys about this age. And this isn't good enough for my boys, and it wouldn't be good enough for these guys. Clearly not. We can clearly do better. The woman on the bottom right-hand side of the screen, she's got a small plastic device. It's low cost, and it filters water. It gives her a 70% chance that she won't develop a debilitating disease from drinking the water through this straw. That means she's still got a 30% chance that she could get a debilitating disease. We can do better. But if you think this is somebody else's problem, it's not. This is Austin, Texas, a few days ago. You had to boil your water to drink it, if you weren't lucky enough to get it off the shelf. On the right-hand image, these guys have been drinking this water for a decade. That's in West Virginia. In the bottom half, you have some of the most well-resourced people on the planet. Hurricane Harvey last year. And I can bet you that they're wondering where sewage water ends and where rainwater starts. I'm David Zuniga, General Manager of the Danish Aerospace Company in North America. I've got a background in developing life support systems for deep space and taking space technologies and applying them to the ground. We're working with the Danish Aerospace Company in Denmark, who has 30 years of human spaceflight experience, developing systems for extreme environments and putting people in extreme environments, and Aquaporin, who's a membrane development technology company that develops water processors. And together, we're the Aquaporin Space Alliance. And we're going to solve this problem. We're going to stop the water crisis in extreme environments. Basic filtering technology today acts through mechanical systems. So it's basically a mechanical grid where you force water through and you reject all the contaminants. So it's really an exclusion device. And the smaller and smaller that you make those grids, the smaller and smaller particles that you reject out. So it's purely through mechanical systems. And really, this is the state of the art. This is reverse osmosis. You have it in most of your homes. And we have it most everywhere we go, restaurants, buildings. So we've developed a technology that uses forward osmosis. Essentially, it extracts water from wastewater solutions. And we've been doing this for about 10 years now. So the thing that makes this technology unique is that it's a biomimetic material that takes the protein from the liver and the kidney, and it's integrated into a man-made material. It's a hydrophilic phobic membrane that helps to bring water in, isolate the water, and reject all the contaminants. You can kind of see a water molecule permeating through the material on the right-hand side. So essentially, we're using nature's water filter. It's found in bacteria, plants, and humans to really act as a water filter to process and reject all the contaminants that we have. So where are we? We have $43 million in assets and financing behind the material. We've gone into large-scale manufacturing. That's our plant in Copenhagen for residential applications. We've then started to spin off different technologies for water, wastewater, semiconductors, dye enhancement, concentrated foods. So the waste stuff that you take out of foods or any sort of processed fluid, it's actually really valuable. It has aromas, it has taste, it has nutrients, and we're really just kind of taking the water out of that. So you get two really valuable products out of it. And the market is huge. It's a $901 billion market, with $30 billion on household goods, and the rest are around $5 billion. So we're in that market. We're doing it today. But the Aquaportin Space Alliance is really trying to focus on the military, world relief organizations, workers in extreme environment, and extreme sports. Like I said, those pictures, there's a problem. Is it just silliness that we're not fixing it? Or is it a technology boundary? Or is it more? Is it socioeconomic? We don't know. But this is our focus area. So today's systems are fairly simple. It's a mechanical pump, and you've got a filter. So just like I explained, it's a mechanical system where you have a grid, and you're forcing water through it, and you're rejecting all the contaminants. Pretty simple, huh? But there are gaps. Those systems remove microbiology. They don't remove some challenging chemistries that are out there. And so when we approached the NSF International about our challenge and the technology we have, they said, wow, you guys do what? You can remove chemistry and microbiology through this membrane system? We don't even know what to do with that. That's a whole new certification category. So today, NSF P248 certifies for microbiology. NSF P231 certifies for municipal districts. We would be something new, something different. It is a new market area. So when I think about filtering water in extreme environments on the planet, I can't help, just because I'm an aerospace guy, thinking about deep space missions. So you put yourself in electrolysis, Sabatier, fuel cell, methane reformation, and sort of this environment where you're trying to live in situ with all the resources that you have, and be really cognizant about all the resources you have. So electrolysis, you're basically breaking water down into hydrogen and oxygen. You're using the hydrogen back into the Sabatier process so you can recombine it with carbon. Maybe you're pulling off metabolic loads or an atmosphere, and you're producing fuel from that. So that goes to an ascent vehicle. And then you're using the oxygen for the fuel cell, which then allows you to produce water and electricity. That then goes to your hab. Then you have some more oxygen go in your hab. And then your crew members, they get some water. So the interesting thing here is that water touches everything. It's fundamental. It touches your ascent vehicle, it touches your ground transportation, your hab module, your crew members. And to close this concept out, it's about 68 tons of water for 500 days for a crew of 4. Let's do the math. At about $10 million per pound for Mars, and 68 tons, that's $1.3 trillion. That's what you'll be spending on your water alone. So today, we're developing our concept. We have the technology behind us. It's in residential applications. It's a solid technology. We know how to apply it. And we're developing a concept for extreme environments. So we're doing the calcs. We're doing the models. We're trying to feel out the market. We're trying to engage customers to try to figure out what requirements we actually have to meet. And if all that works, we have 2 decision gates, one for finances and one for a design sort of concept review, to ensure that we can go on to the next gate. So that would be a prototype development. Once we develop a prototype, put it into customers' hands, we can make tweaks from there and go into the product development cycle. And then from there, production and sustainment. So where do we need the help? We have $43 million in assets and financing behind this technology, and we're using that to launch a new product so that we can solve the water crisis. We need customers to help us make the journey. We want people to know that we're doing this work. We want to know what their needs, their requirements, where they might be able to use the product. Will they be able to use the product? Is this just really a silly problem and are we being silly about it? Or is it a technology hurdle? Can we develop something that does it? So as you go home tonight, wherever that might be, I want you to take a glass of water, or glass, fill it with water, and think about where that water came from and where it's going. As you run your sink, think about the same problem, same thing in your shower, and as you run the dishes. But I want you to raise that glass and celebrate it. We're lucky. It truly is life. Thank you.
So, quick question. If you, I assume you've done this, Houston. If you took you want to desalinate water,
Yeah.
and I assume you've tested it after you've gone through this process. Can you tell us what's still in there? Is it all water, or is there anything else in there?
Yeah, so I mean, there is a challenge with VOCs. There's some organics sometimes that we sort of go through, but we actually, we reject things like ammonia, some of the more standard VOCs, and there are some entrapped gases, but we're kind of working on things on how to tune that. So.
When you get to your product development stage and kind of get the unit presumably down to, let's call it, marketable size, how big will that be? I mean, what do you expect, the kind of normal product development would be?
And you said how big would the product be, or? Okay,
yes.
So, we truly still are in the requirements development phase. We're looking at systems that would be a personal size type system versus that might be for a group. So it might be like 16 people. The 16-person type system might be like a box. That might be a cubic foot. We're looking at the personal size systems. It's obviously got to be lightweight, portable. There are products out there in the market that are within the half cubic foot sort of footprint. So we're really kind of looking at assessing and trying to make sure that we bring something to the table that's going to be normal and adaptable to what the market currently does.
Have you looked at the lifetime of your membrane?
Good question. So we have, and we're hoping to work a little bit more with one of the centers to be able to develop a long life test. It's easily 10,000 liters plus. We're not immune to fouling. Right now, our systems foul because you have mechanical a grid that basically traps bacteria, or traps a lot of particles that then bacteria grow onto. We don't go through the same process because we're literally extracting the water and then flowing the feed through. So we don't have that sort of residence time on the front half of it. So fouling, obviously it's a membrane, it will occur over long periods of time. But again, we're really looking to work with somebody to figure out what a long-term test looks like.
And sorry, Dave, one other question about specs. What about power and consumption, those kinds of things?
Yeah, absolutely. So our goal is to produce 1 liter per hour per person. Power is no power. It's purely mechanical power, or just kind of, in our system, instead of having to force the water through a reverse osmosis grid, and we're not taking that off the grid because we can actually integrate the protein into an RO system. But we'd essentially be able to reduce the amount of pressure that you push through for RO systems. In the forward osmosis system, we would just need you to basically squeeze water and expose it to the membrane and let the basically osmotic pressure gradient difference suck the water out of the membrane. And so that's a natural process that's it's happening right now in our liver, kidney, intestines. So it's essentially a no power solution.
Can I ask, I understand somewhat of your business model. I understand who your client should be, but that's a no-brainer. But who is going to be your actual client? I mean, is it Bill and Melinda Gates? Is it the United Nations? Is it NGOs?
I think we'd like to start off with the military. We know that if, as an aerospace company, we design robust systems, we think that we could probably enter the market there. We then have to kind of start approaching and adapting and evolving our market as we sort of get into it. So, yeah, all those folks you mentioned would be people down the line that we'd sort of look to. Yes.
Excuse me, my area is healthcare. I'm curious, based on the healthcare needs, based on the statements that you've heard, two things. They've already said that water will become more valuable than gold, and that wars could actually start because of the fight over water. But in the healthcare industry right now, have you looked at the use of your system to make sure that the water that's provided to the patients in-house, patients in long-term facilities, patients that are being asked to go home, to live with the water they have, and based on the recent news that's been published, sometimes you can't be thankful for the glass of water that you're putting to your lips.
Right, right. So Aquaporin is actually looking into that, and that is an interesting area because you also have a host of biopharmaceuticals that go into water supplies, and rejecting those is really critically important so that you can obviously give patients the health care that they need.
How well does your technology translate to the biggest users of fresh water, which is agriculture, or is that something that you identify as potential end result?
Sorry, looking for you. Oh, Jürgen Rich. So how well does it apply to agriculture and?
Agriculture uses a lot more water, fresh water than people.
Yeah, yeah. So we actually did start some initial conversations with a university. It was we were looking at some other proposals, and they're highly interested in it. One of the most interesting things we found was that we stripped the water of all its nutrients. You know, it goes in the feed water system, and what you really want in ag systems is you want a nutrient-rich water so you can feed your plants. And so they're really happy to have a system that gives them clean water that they would then just recombine some nutrients into. But you know, the really interesting goal would be to see if you have selective nutrient retention. So you actually, you know, are able to select which nutrients that you can pass through and feed, because then you don't have to have fertilizers and things like that. You just reuse what you have. You're not introducing anything new into that mass balance.
Okay, thank you.
Thank you.